All right, so it's customary, when you give a talk to sort of thank the organizers for inviting you to talk. This is a bit tricky being an organizer, but so I wanted to change that slightly and thank the organizer, singular, for inviting me to give this talk. Not only that, but basically for running the whole program. I think Masaki has already agreed with me that the other two organizers did next to nothing, and the whole conference and indeed the whole program has been run by Dai. So thank you, Dai. All right, so this talk is a bit of an update on the talk that I gave at the previous workshop. I think my main accomplishment between then and now was to actually write it up. So it appeared on the archive a few days ago. And of course, as always, within 24 hours of posting it, I discovered what I'd actually done. So this will contain some new material, which I think is kind of interesting and hopefully controversial. So, so I'm talking about phase transitions. So here's the whoops, I've forgotten which is the laser pointer. I think it's that one. Oh, I see. So we've all heard about phase transitions from high school days. So here's a typical picture of the various phases of water, which I stole from somewhere on the internet, and I hope won't get sued for copyright. But anyway, so you see it's a fairly simple diagram. For the most part, you have water has these three phases: ice, liquid, and steam, and gas. And then there's some critical point up here, and things go a bit wonky up there. But basically, we have these three phases, and an interesting triple point where the three phases coexist. Okay? So this example above occurs as temperature is changed. We all know that if you have ice and you want to melt it, you just raise the temperature. If you have water and you want to boil it, you just raise the temperature. And the phase transition, which is a sort of bulk phenomenon, is a discontinuity in the bulk behavior of the material as you change the temperature. Now, what we're interested in today is spin chains, quantum spin chains, and there's a theorem of Araki that says that the quantum spin chain does not undergo such a phase transition at non-zero temperature. So he shows that in the thermodynamic limit, all of the bulk parameters are actually analytic functions of the temperature, so no phase transition. So what the hell am I talking about? Well, however, at absolute zero, according to physicists, one expects to see what are called quantum phase transitions. So this is what's meant by the term quantum phase transition. It happens at absolute zero, and there's other quantum parameters, other parameters of the physical parameters of the system are varied and at absolute zero. So there's temperature here on this graph. As you go through this point, the phase transition happens at absolute zero. Now, of course, you can't quite reach absolute zero, but what you see is the sort of, as you get closer and closer, you see this phase transition from closer and closer. So this is all a bit on the theoretical side. I think experiment is catching up, but there's still a lot of progress to be done. I'm not an expert on the experiment, unfortunately. But
to fix the vertical line, then there seems to be phase transition at the very temperature in this picture. Yes. So if you go up straight, varying temperature only, then this picture shows phase transition, predicting Araki's theorem.
Well, it doesn't. If you look closely at the picture, this is a very smooth line here going from this one, these phases. So it just looks like a phase transition. It's not a discontinuity. Anyway, this picture was simply stolen from the internet. Maybe they didn't know Araki well enough. But the idea is that the only real phase transition happens at absolute zero. Okay? You can look it up in the famous reference Wikipedia, and you'll see that.
But this may not be a one-dimensional system.
That's true, yeah. Arthur has a point there. This may be about a higher dimensional system where there may be phase transitions.
Well, also Araki
Reckitt's theorem holds for short-range interaction.
Short-range interactions, yeah.
Long-range interaction, even in one dimension.
Sets are off, yeah. In fact, that's what we're going to see. That's what this talk is about, in some sense. Okay, however, so what I want to argue, I'm very happy to see this discussion. I mean, but I'm trying to say something controversial and provocative here, so the more negative feedback I get, the happier I am. So I will argue that, in fact, a quantum phase transition one should see a much more complicated phase diagram. Okay, in fact, it should look more like this. Right, so this particular picture will have three phases. There's a blue phase, the green phase, and the red phase. And according to what phase you're in, and as you go from the, say, the red phase to the blue phase, or the green phase, and so on, then it undergoes a phase transition. Some bulk parameter is actually discontinuous as you go across from one to the other. Okay? So where does this picture come from? Well, you've all seen this kind of picture before, and you will immediately will come to mind all these pictures that we're so envious of Julius sets and Mandelbrot sets and so on, these beautiful pictures. And this indeed is one of them. This is the Julius set of a certain dynamical system, which I'm going to explain in the course of this talk. I'm explain all about it. And let me just remind you that when you have these, this is complex dynamics in one dimension, and when you have these systems, there is the so-called Fatou set and the Julius set. And the Fatou set is an open set, and in this picture the Fatou set is the, well, there's three different Fatou, they're not connected components, they're Fatou regions, the blue, the green, and the red. And Fatou set is an open set, and in a neighborhood of any point of it, the behavior is supposed to be ordinary. Nothing wild happens in technical sense. The iterates are a normal family. The iterates of the transformation are a normal family in the neighborhood of that point. And the Julius set is the complement of the Fatou set, and this is where things go a bit wild. Right? In no neighborhood of a point in the Julius set, which is now the boundary in between these regions, do the iterates of the transformation all behave nicely. So the idea that, you know, what's coming out of these things I've been looking at is that there's these three phases, and as you cross the Julius set, which is now this jagged fractal set, you go from one phase to another. So the phase transition is much more complicated than those nice lines that you saw in the picture of water and ice. Okay, so that's what I'm claiming, and that's what I'm going to try to persuade you of in the course of this talk. So here's another one, another picture of this one only has two phases, a green one and a blue one. And these pictures are courtesy of Kurt McMullen and Sarah Koch, and they were generated using an online available tool called Fractal Stream. And so what we're going to see is that they arise as phase diagrams of quantum spin chains coming more or less canonically. I'll explain the sense of more or less canonically from subfactors of index 2, that was the first one, and 4 cosine squared pi over 8 for the second one. Okay. So now, of course, the million-dollar question is: these phase transitions are certainly real in a mathematical sense. I will define them, and you'll see that there is a bulk parameter that undergoes a discontinuity. But do they actually occur in physics? Well, that's a question I would like to know. This is my prediction, right? For what it's worth, I'm saying that physicists should be looking for this kind of phase transition, experimental physicists. And now we have the number 10 to the 8th. So at this point, I should say that all of this theory arose in some attempt to construct a conformal field theory from a subfactor in some sort of direct way. And the attempt didn't work, and this is sort of what came out of it. But at the end of the day, maybe this is as interesting for the physics of these systems as conformal field theory itself. Okay, and my argument to justify that is this number, 10 to the 8th. Because if you sort of have about that much quantum spin chain, you've got 10 to the 8th, approximately, spins sitting there, all in a row. Okay? And how big is 10 to the 8th? Well, it's nothing compared to the debt of some country in dollars. So the idea is that maybe the graininess, you microscope it a few times, you'll start to see some grainy behavior, and maybe that graininess is better modeled by some kind of, say, two-adic rationals or something than it is by the continuum. Okay? So this is supposed to be provocative, outrageous, and unacceptable. But it certainly leads to some interesting mathematics, and if I keep at it, I may even get some genuine predictions of critical exponents and so on. In fact, I may even already have some. Okay, so there we go. All right, so now let's get down to the talk itself. The language that I'll be using, the vocabulary I'll be using time after time, is that of tensor networks and a slight generalization thereof, which I'll talk about. So I just want to spend just a moment so that there'll be a lot of pictures, and I want to explain the meaning of these pictures so that everyone can understand them. So here is what they're very popular in physics these days, going under the name of tensor networks, where you stick a few tensors in and then you join them up by edges, and then you contract the indices of the tensors along the edges. So here's one. We've got three tensors, T1 with 4 indices, S with 5 indices, and R with 3 indices. And then you contract them according to this pattern, and you get a tensor with 1, 2, 3, 4 indices on the boundary. Okay, that's what a tensor network is, and I've written out explicitly the formula for the answer, which is X, which is a tensor IJKL with 4 indices, IJKL, and this is the formula for it. The first question you ask is, well, how did I put in those indices? Was it in some random fashion? No, it's not, and here's a better diagram of the same tensor network. I put the tensor in a certain region. I contract these boxes to points. I put the tensor in a certain region, okay? And that, by putting it in that region, that tells me where to start putting the indices. So when I put it there, the indices going on T go first, second, third, and fourth. So this is T, I, J, A, D. The A's and the D's are ones that are summed over. And the S index will start there, and the R index will start there. Okay, so just by this cunning device of putting the names of the tensors in the regions, you've taken care of the ordering of the indices, for at least for all the internal points. Then you just have to do something about the boundary, and I just put this yellow dot. So the first boundary index starts here. So this removed all of the ambiguities, everything is set up.
Yellow dots are very hard to see.
Yeah, I apologize for that. Let me shine. There's the yellow dot right there. Now, a more serious objection, of course, is that I'm taking advantage of the planar nature, right? And indeed, I'm really talking about planar tensor networks, which I'm going to generalize soon enough to something called planar algebras. Okay? So that's that. And here's one special one that I want to point out, which is the inner product AB of two tensors. So here's the diagram as a tensor network. There's no boundary points, so we've got to have a number. And the number is this number here. It's just the ordinary inner product, the sort of Hermitian or Cartesian inner product of these two tensors. And if you follow all the conventions, you'll find that that's the right formula. Right, so that was just a bit of vocabulary. A bit more, maybe, is a quantum spin chain. I'm going to be quite general. A quantum spin chain is a linear arrangement of quantum things, each one of which is called a spin, and whose states are given being quantum things. So you need to have a Hilbert space. This Hilbert space is going to be finite dimensional. So for spin 1/2, it might be C2. For spin 1, it might be C3, and so on. So therefore, the state space of the whole chain is the Hilbert space, which is the n-fold tensor product of the small Hilbert space, where n is the number of spins in the chain. So capital N spins, you get this tensor. So all of our operators are living on this Hilbert space, and of course we're interested in a situation where capital N is getting large. You've got more and more spins. All right. Now the chain structure, you see, if you just say tensor product, well, you know, what's the chain structure? Is given, it may be given by an interaction between spins and their nearest neighbors. Possibly a Hamiltonian of the following form. Now, unfortunately, Hilbert and Hamilton have the same first letter of their name, so we have a sort of overdose of H's, and we've got to use all kinds of latex symbols for all these different H's. So here's the big Hamiltonian, which is the sum of little Hamiltonians that give that spin-spin interaction. It's a very short range, it's just nearest neighbor interaction. It could be, I mean, this is just an example. So H, little h, which goes from capital, this curly H tensor, that one, to itself, is a self-adjoint operator giving the interaction between two adjacent spins. Okay? So, all familiar. Now, it's common to impose periodic boundary conditions. So the last spin is connected to or identified with the first, and you can think of the whole chain as being sitting in an annulus. And I think probably in this talk, every single picture I will have implicit periodic boundary conditions. So in terms of tensor networks, the action of this Hamiltonian, the big Hamiltonian, on the vector in H is given by this sum, and I think maybe this is the only one in which I haven't got periodic boundary conditions. The sum only goes up to n minus 1. I think it have to go up to n and modulo n. Anyway, so this is just to work our definition, work our formalism of tensor networks. The vector psi is also a tensor, right? It's a tensor with capital N indices. And these little h's are also tensors, and this is the vector psi. Psi has n, capital N boundary points. H of psi also has capital N boundary points. And this is what it looks like in tensor network language. Okay? So now I just want to, we're going to be talking a lot, the main focus of this talk is going to be on transfer matrices. So I want to remind some of you and show for the first time to some of you that there was a beautiful way of generating these Hamiltonians, like the one above and many more, and it came out of the St. Petersburg school, Fatou, of course, in the 1980s. Fatou and many others in St. Petersburg. The idea is that T of lambda, so this is little t, now we've got lots of t's for transfer. T of lambda is an element of end of H. So it's the same, little t is a beast of the same nature as little h. It goes from H tensor, oh yes, sorry. This should be end of H tensor H. I thought I got all the typos out, but apparently not. T of lambda is an element of end of H tensor H. No. I think I screwed up all these H's. This is just a little local thing. Anyway, let's see the picture. So here's what we're really after. This is the capital T. So this is all garbage, but this is the right picture. So I've taken this T of lambda and I've just called it lambda to eliminate one of these T's, and this is what capital T of lambda, the transfer matrix, looks like. This is a tensor network. These are, according to our conventions, we just put the tensor in each of these parts. There's periodic boundary conditions, and so this gives a mapping with these boundary points at the bottom to these boundary points at the top. So it's an endomorphism of what I called endomorphism of this H here, right? Endomorphism of this H here. So going back, the little t of lambda, the only typo here is that that should be end of H tensor H, not H. So that's the transfer matrix.
T, capital T accent in what?
Capital T goes from this math frac H, math frac H,
Yes.
this one here, to itself. Okay. So that's the big kahuna, the big T of lambda. Right. And so it's the idea is that lambda is just a parameter, but the parameter might have lots of components to it. It might be the whole matrix algebra. But it's traditional to write. So let's suppose that T of 0 at some reference point 0 in the parameter space, T of 0 is just this very simple tensor here. Right? For those of you who don't know this tensor language very well, this is the tensor. This is called typically we would call it a Temperley-Lieb tensor these days. It's the tensor which is 0 unless this index is equal to this index, and that index is equal to that index, and otherwise it's 1 if they are all 1. Okay. So it's some version of the identity drawn in some funny way. But if that's true, then there's a calculation which I think I did last time I gave this talk, but I just want to save a bit of time by skipping it. All it is the Newton, well, no, the Leibniz rule for product, differentiation of a product. And it says that T of 0 inverse T prime of 0 is this sum, there's a sum missing, I'm sorry, sum over I, with H here, where H is this little thing which is the derivative of T at 0. So T was this T of lambda, and we've differentiated at 0, and we've got this thing. So we get, from this transfer matrix, we've come up with a local Hamiltonian, simply by differentiating. So that's a wonderful thing. But furthermore, part of the whole business is that the matrices T of lambda, little t of lambda, are supposed to satisfy, or are said to satisfy, the Yang-Baxter equation, which I'm sure we'll be hearing a lot more of in this conference. They're said to satisfy the Yang-Baxter equation if for every lambda and mu there's a third value of the spectral parameter such that this diagram holds. So this is once again a picture in the language of tensor networks. Don't need to spell it out anymore. We have lambda, for every lambda and mu, there is a sigma such that this is true. And the thing to observe is that sigma has gone from the top to the bottom, and as it goes down, it switches mu and lambda. That's its role in life. So that's the Yang-Baxter equation. And if that's true, there's another beautiful and simple argument that implies that these transfer matrices, T of lambda and T of mu, for different values of the spectral parameter, with periodic boundary conditions, actually commute. So that's an amazing thing. Very pretty argument. And here's the picture of that. This is T of lambda, T of mu equals T of mu, T of lambda. So here is T of lambda, here is T of mu, here I've done this one first and then that one, and the answer is that that is the same as this one and this one. So this little local condition on lambda and mu implies this global commuting condition on the transfer matrices with periodic boundary conditions. Okay, any questions on that? So this is this whole quantum inverse scattering method that was very, very popular, and still is, I guess. So what this means is that T of lambda is a package. So it's supplied us by algebra and calculus with a large family of operators, in particular the Hamiltonian, the local Hamiltonian, that was given by T of lambda by differentiation. Gives you that, but not only that, it's got a whole lot more stuff in it. In particular, it gives you a high dimensional algebra of matrices T of lambda which actually commute on the nose with the Hamiltonian. And then maybe by differentiating twice you can get slightly longer range Hamiltonians and fiddling around. And you can get a whole infinite family of Hamiltonians, and you can get common eigenvectors, and this is sort of the easy part of the quantum inverse scattering method. Then you have to try to get exact formulas, or formulas that you can control for the eigenvectors and eigenvalues as functions of the spectral parameter. That's where it gets much more difficult and deep, I think. But so first of all, a quick observation which will tie in with Arthur's talk in some sense, I'm sure, is that all that went into the arguments so far, well, unfortunately I didn't do them, but if I had done them, you would have seen that all that went into these arguments, the arguments being this local Hamiltonian and the commuting transfer matrices, all that went into them was the pictures. All I did was manipulate pictures, manipulate this visual kind of mathematics. If one can set up a framework where the pictures make sense without referring specifically to tensor networks, the arguments will hold you will be able to get your local Hamiltonian, and you'll be able to get your commuting transfer matrices. So this has been done, and one such framework grew out of subfactors and is known as planar algebras. So all of these pictures, we just draw the pictures, they have the same kind of way of working with each other, but their interpretation, how you read them, is not quite the same as these tensor networks. You have to be a little bit more abstract or concrete and a little bit different. So this is planar algebra. So what I'm saying is, I hope you've all absorbed what it means to have a tensor network and how to manipulate them by joining, gluing them together. Well, you can do the same thing in a more general context known as planar algebras or various categories, tensor categories and quantum groups and things like that. So a lot of the equations I will solve, we're going to start solving equations eventually, actually in the framework of planar algebras. And the reason is the greatly increased flexibility will have some advantages. In particular, there's a parameter which, if you work in tensor network, will be fixed to be 3, and then all of a sudden, by jumping to these planar algebra, these categories, you can have it being a lot of different values. And we'll see how that arises later on explicitly. All right, so here I'm going to be also a bit controversial, hopefully. And so what I'm going to say is, forget the Hamiltonians and all of these stuff. What I want to do is take the transfer matrix itself and consider that as being the fundamental physical object, mathematical object representing the physics. Okay. So I'm going to say, well, all these Hamiltonians are all very well. What I'm really interested in is this whole package, the Hamiltonians and the transfer matrix. And I'm going to study how that behaves. I'm going to give a justification for that in this new context shortly. Okay, so let me be quite clear. We're throwing out Hamiltonians and the usual kind of thing. We're saying what's determining our physical system from this point of view is the transfer matrix. And the atom, the interaction parameter will be that spectral parameter in the transfer matrix. So one of our ambitions in what follows will be to construct transfer matrices with continuously varying spectral parameter. So one of the important things to see here is we don't want this just this braid thing. That's not enough. You've got to have the honest spectral parameter so you can do calculus and have C-phase transitions in it. So we want to construct transfer matrices which are compatible with certain scale invariance properties. And now I'm going to get to the scale invariance part of the talk. But I just want to leave this with a mantra. Since the Hamiltonian is the infinitesimal generator of time translation, we're going to take this mantra here coming up. The transfer matrix determines infinitesimal time translation. Right? The Hamiltonian was derived from the transfer matrix by calculus. The Hamiltonian is the generator of time translation. And we're going to phrase that as the transfer matrix determines infinitesimal time translation. Nothing controversial about that. Okay. All right, now we get to the more penetrating parts of the talk. So the following construction was originally motivated by a quest, so far unsuccessful, to construct a conformal field theory directly from a subfactor. It can also be thought of as a reversal of the idea of block spin renormalization due to Kadanoff-Wilson. So, we've been hearing all of our lives, some of us, this dogma that, at a critical point of a physical system, there's some kind of self-similarity on all scales. Okay, and some of us even used to play around with simulating Ising models on their computers back in the days when we had these Sun 350s in our office, and we, zoomed in, and we did see indeed at the critical temperature of the Ising model that the patterns kind of looked the same at all different scales. So it's an idea that has stuck with me for a long time, and the idea of this block spin renormalization was to take a bunch of spins, say 4 spins in a two-dimensional Ising model, block them together and try to get some kind of Hamiltonian or something that was actually give you the same parameter, same kind of behavior with the block spins playing the role of single spins. So that's what we're going to do in the quantum spin chain. But because of the motivation, it's going to actually come up in reverse. We want to construct a Hilbert space for our supposed conformal field theory to act on. And what subfactors give us via the planar algebras is for each finite subset of the circle, give us a Hilbert space. Okay? So we want to start with Hilbert space for each finite subset of the circle and get a big Hilbert space. The ones for the finite subsets of the circle are finite dimensional. We want to start adding points all over the place, let the Hilbert space grow bigger and bigger, In the end, it's got to be an infinite dimensional Hilbert space, and on that infinite dimensional Hilbert space, we would like to see conformal field theory. That was the plan. So the fundamental thing we need is how do we add another point to, given the Hilbert space for n points, how do we add another point? Well, planar algebra gives you the way to do this, provided you have a certain element in the planar algebra. So we will do this. We're going to double one of these spins by giving ourselves a privileged element y in the endomorphism from h to h tends to h, or in planar algebra language, that would be called a 3-box, because it's got 3 boundary points. So here's our y is sitting there, and the adjoint of y, by the way, would be exactly the spin blocking operator. If we would block 2 spins and come out with 1 spin, and that would be a map from h tends to h, and the isometry condition is this one, this tensor network here, y star equals the identity. All right, and just for one last time, explicitly, I've written out what this actually means in terms of indices. All right, so we're going to give ourselves one of these y's, and what are we going to do with it? Well, we're going to use it to create from these finite dimensional Hilbert spaces an infinite dimensional Hilbert space. The way that's going to go is as follows. We're going to take Hilbert spaces, some kind of h sub n of dimension, the initial Hilbert space to the 2 to the n, by embedding this one and this one. So we take a vector here. This is a vector in the Hilbert space with 4 boundary points, so that's going to be the dimension of h, the initial h to the 4th, and we're going to double all these spins by sticking in this y, and this psi is going to give us a vector in the tensor product 8 times now of the basic single spin Hilbert space. Right? And then we're going to continue, iterate this process, and we're going to end up with, since y is an isometry, we're going to end up with an infinite dimensional pre-Hilbert space, and then we'd like to maybe complete it, get a Hilbert space. Now if we choose a vector omega in h, which for some reason is special, then then that is going to define a vector in each tensor power of h via the above embedding. So what we've got is we've got a what's it called? It's called a direct system. That's a direct system of Hilbert spaces. We have this one, then it's embedded in this one, and that one, and then the big Hilbert space is the inductive or direct limit of these Hilbert spaces. So given a vector right down here, it actually defines a vector all the way up, and therefore a vector in the limit. And for perhaps no good reason, we're going to call it the vacuum vector, some kind of reference vector which is sitting in this infinite dimensional space, but is actually in the very small one. So, here we go. The Hilbert space H is defined as the direct limit of the above increasing sequence of Hilbert spaces, and will be called the semi-continuous limit. So this is what I was saying, maybe if there's only 10 to the 8 spins, the continuum might not even be the best model, so we're going to call this the semi-continuous limit of the quantum spin chain. And I
assume some kind of co-unit property of omega or y being co-associative?
Nope. If you do, I could, but that would limit it would limit my examples, and B, it would, I'll come to that. So there's something about the Thompson group that would force, which would not be so good. Yes?
How does the Hilbert space depend upon the transfer matrix?
Let me come to that. I'll soon answer that point in great detail. So Osborne and Tobias Osborne and Guifre Vidal, I've discussed quite a bit with them, and this is where this name semi-continuous limit came from. And now just a picture for what the vacuum vector looks like. Here it is. So here's omega, and here it is embedded all the way up in this one. So we're to think of omega as being, this thing where we've just gone infinitely up, and there's some kind of reference vector. When you do an infinite tensor product, we all know from von Neumann that you need to have a reference vector, and the vectors in the infinite tensor product are sort of perturbations of the reference vector. Well, this is a similar infinite tensor product. We've got this omega, and the vectors in the semi-continuous limit are somehow finite perturbations on this vacuum vector. So that's the language. Now all of these y's are getting redundant, so I'm going to just suppress them basically. I'll drop the y's. We'll tend to suppress the y. Okay? Now comes a major part of the program, which I haven't emphasized today, but it's there. Thompson's groups F and T of homeomorphisms are defined by local scaling transformation. I'm going to say exactly what they are in a second. Act unitarily on the semicontinuous limit. So this is a theorem. It's not all that hard to prove, but it's a pain in the neck if you do it this way. Anyway, there's a much more elegant way to do it, but I'll do that later. And it acts, the Thompson group acts by local scaling transformations. So that's sort of what we're after, right? We want to, Kadanoff-Wilson say, at a critical point you should have local scale invariance. This Thompson group is actually the group of local scaling transformations. So in order to express ideas of scale invariance, we're going to express them in terms of this Thompson group. Yes? Question?
Excuse me, I haven't understood what happens to the transfer matrix in this business.
It's coming back, yeah. Very soon.
Scaling without interaction.
Very soon. Yep. I'm going to come to that. I will address that question. But let me just, I just want to tell you what this Thompson group is. Thompson group F is the group of all piecewise linear, orientation preserving homeomorphisms of the unit interval whose non-smooth points are dyadic rational. Oh, sorry, I should also add that there's only finitely many non-smooth points. Otherwise the group's a bit too big. So it's, the unit interval is chopped up into finitely many subintervals, and on each of which it scales either up or down the slopes. Okay. And Thompson's group T is the same as F, but it's defined on the circle. So in particular, Thompson's group T contains rotations by dyadic rationals. Okay, so you can just rotate the circle. All right, now I'm going to start to address this question of the what's the transfer matrix and what I've done so far with the semi-continuous limit actually has to do with quantum spin chains. The point is that at this point the semi-continuous limit consists of these trees, and you can take one of these trees and shake it around and the branches will go all over the place. So what does that have to do with a quantum spin chain which respects the order of the spins, the order of the leaves of this tree? They're supposed to come one after another. Okay, but Thompson's group as an abstract group doesn't impose any structure on that. However, here's the point. Sorry, I have to I'm stuck with this is the trouble with beaming presentations. I would like to go somewhere else, but I've got to go here right now. People in the block spin renormalization game encountered the same difficulty, right? People, there's this density matrix renormalization group and so on. They came across this tree also, and they introduced the fact that there's no, the being next to each other physically on the chain has nothing to do with being next to each other on the tree. Evenbly and Vidal invented the mirror. So this is the multi-scale entanglement renormalization ansatz. They're very proud of their names, which introduces these so-called unitary disentanglers to tie up the branches of the tree. So this is a picture stolen probably from one of Guiffre's talks. So you'll see that we have the same tree that I'm talking about. There's this root here, and at these points, at these triangles, you get the spin doubling. But to tie the whole thing together so that it's not just these trees wafting in the breeze, these branches wafting in the breeze, they put in these so-called disentanglers, which are supposed to be unitary operators, so that after you've done a spin tangling, you actually tie this one to its neighbor. Okay, and so this means that this long-range interaction, which is going along the tree. So the point is that if you take 2 points at a large Euclidean distance in the chain, they could be quite close along the tree, like logarithmically close. And similarly, 2 points that are very close to each other spatially could be a long way apart on the tree. Okay. So this is what they introduced these disentanglers for. Take care of this, too long distance interaction. And they claim that they obtain good numerical agreement with conformal field theory by optimizing the disentangler. So, as someone has observed, there's no constraints yet about what I use for y, and for them for the disentangler either. So they get some kind of optimization over that space, and they calculate endpoint functions and so on, and they claim to get a good numerical experiment with critical exponents in CFT. Okay, so we're going to stick with the tree just to see what comes up. We're not going to. Yes, question.
Which CFTs?
Well, as far as I know, I could only say for sure in my conversations with them, but for the Ising model, the continuum limit of the Ising model. You see, this is one of the problems for reasons for not going after the mirror straight away, is that all of their results are numerical. Okay, and we want to have theorems. We want to say this subfactor gives this CFT. So, you know, this is just not going to be quick enough. But so, in some sense, just to be perverse, I'm going to stick with the tree. I'm going to stick with the tree. No longer expect to get CFT. Okay, because of this strange long-range phenomenon, two long-range things from the tree. But maybe because of my 10 to the 8th argument, it might still be relevant to a quantum phase transition. Okay. Now, here's the point where everyone's still wondering. I think, where is this transfer matrix, and you know, how does it go? Well, in order to think of these points on a line, instead of just the branches of some tree, some infinite tree, as soon as you say my Thompson group elements are homeomorphisms with a circle, then you've said these are the points on the line. They're not just the leaves of some abstract tree. Okay? So what I'm saying is, as soon as I consider the Thompson group action, and thinking of the Thompson group action not as in some abstract group, but as a group of homeomorphisms, then I've recovered the order of the points on the line. So this is sort of important, and we'll see it in practice in a second, if we have time for all this. So we want to investigate properties of such states produced by trees. Are such states relevant for physics? Well, I've said maybe out of quantum phase transition, and some maybe quantum physics. All right. So, but now I want to ram home this point that it's the Thompson group that imposes the structure of the line, the structure of the spin chain, by doing a calculation. And as a sort of magic output of this calculation will come the transfer matrix. We'll be forced to consider it as soon as we throw in Thompson group, in fact only rotation group, and the tree. Okay, and so this is how it goes. So what I want to do is rho of 1 over 2 to the n is just a rotation by 1 over 2 to the n. And I want to take two vectors in my semicontinuous limit and calculate this inner product. So if we would do it, the reason, of course, for doing this calculation was if this was supposed to be a continuum limit, then this should be going to, it should be just going to the inner product between psi and eta, right? This rotation by less and less should be going to the identity. Well, we're going to see by manipulating transfer matrix that in fact it doesn't do that. And you know, that's why I had to abandon this approach to get CFT. All right, so it's all in a picture. I'm going to draw the picture for this thing, for this inner product in tensor networks, and here it is. Here it is. So here we have psi. Remember, we're trying to rotate it and then take the inner product between psi and eta. So I've taken psi. I want to it's in some, you know, relatively small vector space, but I want to rotate it by a tiny little bit. In order to do that, I've got to embed it up and then rotate by that tiny little bit in a much higher Hilbert space approximation. It's the same vector. So you'll see that what this picture consists of is psi up to halfway, and then it's just been shifted along one little unit, and then there's eta upstairs to complete the inner product. Okay, so this is just simply the tensor network picture of that inner product. Now look at these blue things. If you look inside all those blue circles, you see exactly the same thing. And if we call that thing x, then this picture becomes the following picture. Here's psi, and here's all of these x's, and there's eta. But what is this thing in the middle? This thing with all of these x's? That the transfer matrix by definition. Okay? So the lesson is that the inner product of the rotation by 1 over 2 to the n of psi with eta is given by the transfer matrix. So the transfer matrix has forced itself on us. And once again, the transfer matrix gives us linear order on the spins, and it was a consequence of the linear order imposed by the Thompson group itself, considered as homeomorphisms. All right. So, but now this is where the neat thing happens. So first of all, the mantra, the transfer matrix determines infinitesimal space translation in this case. As n tends to infinity, you get small. If we're in one dimension and time equals space, then that's the same mantra as we got from the quantum inverse scattering method. Infinitesimal space translation is given by the transfer matrix, but now it's come up in this topsy-turvy fashion, so we've got this different world. The ingredients of QISM and conformal field theory seem to crop up, but they get all mucked up somehow. All right, but now we have some fun, because if we go back to that picture, we'll see that it consists of all of these little x's, and if we isolate a little box there, then it consists of a whole lot of these ones, little boxes. And so if we call the renormalization, quadratic renormalization map R of x, we call it putting things in this little box, then if we apply that, we will get this picture. Okay, so now if you compare this picture, so y is this renormalization map applied to x, and if you compare this picture to the previous one, the one thing you'll notice is that there's half as many x's, half as many y's as there was x's, right? Don't have to look too hard to see that. So if we keep iterating that, then we'll get rid of all of those x's, and we'll get down to simply the inner product of psi with a transfer matrix by itself with eta. And we see, in fact, that this is exactly what I just said in words. This is written out. We iterate this renormalization map n times, and we get the formula, explicit formula for rotating by this very small factor in terms of iterating the transfer matrix. So we see that we have to understand the dynamical system defined by the renormalization map. Now it's important, I didn't emphasize this at the time, but let me go back a bit. This map R is a homogeneous quadratic map from the space of tensors with 4 indices, which we call 4-box space in planar algebra language, to itself. So it's a completely classical dynamical system. That's what I'm saying. Nothing quantum about this. It's from some finite dimensional, vector space in this case, to itself. And we're iterating that, seeing what happens. Okay, but it's not linear, so we're going to have some fun with that. All right. So now, in order to get any further, we're going to need to put ourselves in a context where we can actually do calculations. We have to have a model, and we have to have an explicit spin doubling map. Now we're going to take advantage of certain planar algebras where there is no choice in the element y. Like one of the problems was, what do we choose for y? You know, without any physical intuition or anything, what are we supposed to choose for y? Well, there are categories, or subfactors or something, where there is no choice in y. So that's fantastic. We'll start with them, and all the possible choices of y's are gone. So if you're not happy with planar algebras or categories, then you can stick with tensor networks. In this case, the dimension will be 3, and all of the tensors will simply be the fixed points by the action of SO3. And if you do your Krebs-Gordon rules, you'll see that there is indeed a unique choice of tensor in this threefold tensor product, which is unique up to an irrelevant phase. Okay, now what the planar algebras or quantum groups actually allows you to do is put in, deform the 3, right? And you get some continuous and discretely varying quantum parameter. In this case, the y is rotationally invariant. You can check that, so you can suppress it. Doesn't matter in the pictures, and just use a trivalent vertex. So, and there's a very interesting paper by Morrison, Peters, and Snyder on categories generated by a trivalent vertex. This is one of the simple ones. And we can now calculate this renormalization map explicitly. So remember, this renormalization map is a classical map, a quadratic function going from some finite dimensional vector space to itself. In fact, because we're taking in the invariant tensors, if you like, that space on which it's acting is going to be, by your Krebs-Gordon rules again, of dimension 3. So we've got something just mapping a quadratic map from a three-dimensional space to itself. To do the so here's a typical tensor with 4 legs. It's a three-dimensional space. It's spanned by these 3. Or actually, this is y. You see, this is constructed from the y. And we have Morrison, Peterson, Snyder, or anyone else gives us a complete set of relations to do the calculations. What we find is our renormalization map is explicitly this map here. So this is just a calculation, which we do by hand. It's a little bit complicated, but maybe we haven't chosen very good parameters. Renormalization map of A. A was this arbitrary linear combination of the basis elements. It's this homogeneous quadratic applied to A. So this is the dynamical system. It's, you know, by dynamical system standards, it's not very complicated. What we want to do is iterate it. We'll just keep applying it. And note that the D in the above is the quantum dimension, which can be 4 cosine squared pi over n, and D equals 3 is the case of the classical SO3 invariant thing. So we see that the rotation, the infinitesimal effect of rotation, is determined by iterating the above quadratic transformation of R3. And some calculations show that if we start with x, this is what we need to start with to get the rotation, we iterate, and then we get different behaviors. So these are sort of different universality classes coming up from this very crude analysis, but they can certainly happen. What can happen is, as you iterate, x was already fixed, or at least almost fixed, by R itself. So in fact, R would just flip backwards and forwards between this and its the other obvious version of it. That happens exactly when D equals 2. If D is bigger than 2, then what you find is the limit of R to the n of x goes to 0. Okay? So R to the n goes to 0 in the second case, but not in the first case. So they're somehow qualitatively, quantitatively different things. And it's hard to know what to make of these results, but certainly there's different qualitative behaviors of the states. So now I want to make things more quantitative, and let me go through this very quickly. We can just not look at the details too much. If you think of Stone's theorem on one-parameter unitary groups, it says, a complicated way to say it is, given a strongly continuous one-parameter unitary group on Hilbert space, then since it's continuous, this quantity here tends to 0 as t tends to 0, but you can renormalize it to get information out of it, and you get the generator of the one-parameter unitary group by doing this, dividing by t. And this is how you would get it as a quadratic form in the sense of Barry-Simon, or a sesquilinear form. Thus, in quantum mechanics, one obtains energy and momentum from time evolution and space translation. Well, here we've got these rotations, and all of a sudden this thing is not tending to the identity, it's tending to 0, damn it. But maybe we can still renormalize it, scale, blow it up, and actually get some operators out of it. Okay, that's a typical thing a physicist would do. And indeed that works. It turns out that we can figure out how fast it goes to 0, renormalize by it, and get these quadratic forms. So this is just this thing going to 0, but then we blow it up by dividing by this thing going to 0, and we get 2 quadratic forms on the Hilbert space, the pre-Hilbert space, such that the limit is either this one or this one. And these should be called the topsy-turvy momenta. I call these 2 operators or quadratic form, because momentum is the infinitesimal generator of space translation, and these are the sort of topsy-turvy generators of space translation. Right, now the 2 quadratic forms, you get them, you get explicit formula or moderately explicit by iterating this thing. All right, now I want to skip through a lot of stuff, but I just want to say that I discovered fairly recently this other kind of phase transition in the quantum parameter D. And it turns out that when D is in this discrete series, there's these 2 points, these 2 topsy-turvy momenta, and they get, but then as you increase D beyond 3, which is where the continuum starts, and if you get up to this point 3.5 approximately, then these 2 operators actually coalesce, and from then on you get the same one. So there's a phase transition in D space with these topsy-turvy momenta.
Sorry, just to put, since you flashed D so quickly, can
Sorry.
you just see which values of D correspond to which models?
So
About what icing is D equals 2?
that's pretty much right, yeah. But it's all it's not icing actually. No, it's, hang on. The D is 4 cos squared pi over n minus 1. So D equals 1 would be Ising, but Ising doesn't exist. It's been cabled once.
In the Potts language, then D
D is Potts
Q
model, yes, right.
minus 1, and then...
In the Potts model language, I think D is Q on the nose. D is Q.
Not Q minus 1, because where it goes to the continuum is the 4-state Potts model, right? So D is Q minus 1.
Let's argue about that. Sorry, I'm not.
No,
Yes. Yeah. So here's a picture of the interesting points in R2 for the projectivized renormalization. I'm going to skip this because I want to explain those original pictures, and I'm already basically out of time. So I'm just going to skip this. This is just looking at that dynamical system, that explicit one that I talked about. It's in real space, and there's this repelling sort of something. So, and then I'm going to skip this. And now I want to get to rational functions of one complex variable. So right at the beginning, I hopefully got you interested by flashing up these pictures of dynamical systems which you see in the iterating these people's world of Julia sets and so on. I want to see how we get them. So for this, we're going to the SO3 thing had these two parameters. The space it was acting on was 3-dimensional, P, Q, and R. Then it became 2-dimensional when we took a projective, but it was still 2-dimensional. But we could draw pictures because it was real. Okay. Now we're going to not do the SO3 invariant stuff. We're going to do SU2 invariant stuff. We're going to take a spin-a-half system. So the space that we'll be acting on will be 2 complex dimensional. Projectively, that becomes 1 complex dimension, and that's where the rational functions live and move and have their being. So we want to get there. So in order to do that, instead of spin doubling, I'm going to spin triple. So I'm going to replace a spin by 3 spins. So the Y will now become this fork with this sort of devil's thing with tensor with 4 legs. And it will be an SU2 invariant tensor. So we'll be in the ordinary temporally Lieb planar algebra. And we can choose this devil's fork to be anything satisfying the unitarity condition here. But now, the renormalization transformation, before it was a homogeneous quadratic, now it's a homogeneous cubic, because we've tripled things, but it will be in the small dimensional space. The real price we pay is that it's no longer unique. There's a 1 parameter's family's worth of choices of the spin tripling operator. Okay? Which means that we should also see a Mandelbrot set from the sort of interesting dynamical systems. So now, what I'm going to do is I'm going to choose the braid, we can just choose a crossing here for this fork, and I'm going to choose delta equals root 2, which is called the Ising model. So in this case, this picture I'm going to do is the Ising model. Okay, and here's the transformation. As I said, it's a homogeneous cubic, which I've made projective, and this is what it is. The cubic on top, cubic on the bottom. Right? But it's a rational function on the complex numbers, on the projective complex numbers. And this is the one, here's its Julia set and Fatou set. That's this one that I did at the beginning. So we have these 3 phases, the green, the blue, the green, the red, and the blue, and they go to different, under iteration, these regions go to different fixed points of the renormalization transformation. And finally, I'd just like to end, only being 5 minutes over time, with what is it that undergoes a phase transition? After all, if we're talking about physics, we're supposed to have a free energy per site, partition function that actually has a discontinuity. So what is it here? So now I'm going to explain that to you. So I'm being honest here. Remember, we're considering the spectral parameter in the transfer matrix as a spin-spin interaction parameter. And here it is. So if we have lambda is p times one of these temporary leaves plus q times the other, and r lambda is this, and so on. And here's the projectivized version. So here's a theorem. So if q over p, that's the ratio of the coordinates, that's what you need for it to be projective, then the limit as n tends to infinity of what, so this is the logarithmic growth rate of the transfer matrix with the renormalized n times parameter with the vacuum, is the log of p plus this, which is sort of obvious quadratic thing, plus this correction term, where I get it by iterating the renormalization transformation. So you see that depending on which part of the Fatou set q over p is in, these renormalizations will go to one fixed point or another fixed point. So in these two different Fatou regions, you're going to get different values for this limit here. And as you cross the Julia set from one of these regions to another, this function will undergo a major discontinuity. So that's the phase transition. That's what I'm talking about. That's a proof that's only for me to remind me how it worked. And finally, so this quantity, which I've written here for the theorem, is actually a macroscopic variable, depending on the parameter lambda. It's the limit as the length of the chain tends to infinity of the vacuum expectation value of the transfer matrix with spin-spin parameter lambda per site. That's what it is. So that's exactly what a physicist would tell you you've got to calculate to get the thing that might undergo a phase transition. So we see, just to end, if lambda stays in a given basin of attraction of the Fatou set, it will very smoothly because of this normal family condition. But shifting to another basin of attraction, going across the Julia set into another basin of attraction for Fatou, it will undergo a discontinuity. So that's the kind of phase transition that, according to me, according to this argument, should be occurring in quantum phase transitions. Okay, oops. So that's the end of the talk. Thanks.
Are there any questions or comments? Can you show the thing that we saw subliminally with L0 on it?
Oh, right. So that's, so you know, there's some dark clouds on the horizon. I presented all the pretty parts of the picture, but you know, the rotation in conformal field theory is L0, right? But, well, maybe since we haven't split to left moves and right moves, it's L0 plus L0 bar. So the higher LNs, which we would like to see in this topsy-turvy LNs, will come presumably from the Thompson group. All I've done is I've taken the Thompson group and taken this tiny little part, the rotation. So that's like taking the diffeomorphism group and only looking at rigid rotations. All the other ones should somehow come from higher LNs. The second subliminal point is I also just did rotation by 1 over 2 to the n. I cannot prove that the limit as the rotation tends to 0 of this inner product is actually 0. I can only do it for rotations by 1 over 2 to the n. This is not completely because I'm stupid, but it has to do with another thing that, you know, that a physicist will say, well, you know, all you've done. I mean, if I show this to Lieb or Baxter, they'll say, you know, well, isn't that trivial? In some sense, that's true. But if you start to calculate more complicated things, then you have to really get into the guts of the transfer matrix by taking its powers, right? The transfer matrix by itself, not that much, but when you start composing it with itself, and you need to do that to get these rotations other than 1 over 2 to the n. So I'll stop there again. Yeah, question?
Yeah, in the 90s, physicists were solving statistical mechanisms model on fractal lattices.
Yeah.
You're probably aware of it. I mean,
yeah, unfortunately,
probably this was the same kind of calculation, right? A sort of discrete renormalization, and they get these Julia sets and all. Any comment on that?
I may simply be rediscovering what they did. That's possible, but it's I don't know. I'll have to look into that a bit more carefully. Yeah. That's a good point. I mean, the third comment there was how to get this. I can do this and get it on a two-dimensional lattice with some kind of homogeneous transfer matrix this way, but then non-homogeneous in the other direction. And this limit comes up exactly as that.
Another comment I had, or question, sorry, Bob. You've talked a lot about the ground state, but for a physicist, the ground state is the state of lowest energy.
I didn't call it a ground state, I called it a vacuum vector.
Sorry, I'm sorry, you're right. So it's defined as being invariant under SL2C?
No, it's not. No, it's not. It's not. As we saw, it's not even invariant under the rotation. So it's a vacuum vector in some.
It's just a good.
Just a reference vector. Yeah. Cool.
So you listed these values of D, that have special things, well, in lots of contexts. But where did the special properties enter into these calculations? In other words, why do you have to take D to be one of those values to get? Or do you? Might they work for any D?
Well, I mean, this goes back to when these planar algebras, when there's the inner product positive definite. If you want to have Hilbert spaces, then you're forced to take these values. If I took D between, in this last case, between the square root of 2 and the golden ratio, then all the formulas would work, but you wouldn't be working on a Hilbert space. Okay.
In your final example, you said you had a one-parameter family of choices for your y's. Does anything meaningful change if you make a different choice than the one that you did?
Yeah, I mean, if you look at these pictures, they change. They change the set. They change the number of phases. They change the rate.
But the fact that your reference space is not rotationally invariant, or so
that doesn't change. No.
It doesn't fix that.
No, it doesn't fix that. Well, one of the values d equals 2. It was almost fixed, actually. That was the value where it just flipped around between two different values, so it's almost fixed, but not in any useful continuous way. So, right.
Any more questions?
The lattices are not fractal lattices. The lattices are ordinary lattices. It's just that there's an imposed fractal thing by this scale invariance.
Any more questions or comments? Thank you again, Vaughan.